Hi, I'm Jeff Groh, and this is your Calculus 2 Exam 3 review. We begin with a sequence of problems where we are to determine the convergence or divergence of various infinite series. And in particular, we're to state the test used to determine convergence or divergence and to show your work. Determine whether the alternating series converge absolutely or conditionally. On problem 1a, we begin with the sum as n goes from 1 to infinity of 1 over n. I don't need much work on this particular problem because this one is a series that has a name. This is the harmonic series. And it diverges. This is all I need to see on this problem. Don't try to do too much. The next problem is the sum, as n goes from 1 to infinity, of negative 1 to the n divided by n. Again, I don't want to see too much work on this particular problem. This is the famous alternating harmonic series, and it converges conditionally. On part C, we have the sum as n goes from 1 to infinity of 1 over n to the 1.001. I only want three things here. I want you to state that you're using the p-series test. P is 1.001, and that is greater than 1. Greater than 1 is the condition that tells you the conclusion, and the conclusion is that the series converges. The next example is the sum as n goes from 1 to infinity of 1 over n to the 0.999. Again, you should use the p-series test. P is 0.999, which is strictly less than or equal to 1, and therefore this series diverges. Just give me these three things. Then we have the sum as n goes from 1 to infinity of e to the n divided by n factorial. You can see we're pitting exponential growth versus factorial growth. Factorial growth should win. We expect that this series will converge. The test, since we have a factorial, is the ratio. The test, since we have a factorial, is the ratio test. We'll take the limit as n goes to infinity. The ratio test uses the formula an plus 1 over an. That will be the limit as n goes to infinity. E to the n plus 1 over n plus 1 factorial, n factorial over e to the n. You can see that n factors of e cancel, but more significantly, all but n plus 1 factors in the denominator. It follows then that the limit is 0, which is less than 1. That's the condition we need to state, and therefore this series converges. Next we have the sum as n goes from 1 to infinity of 1 over n times n plus 1. While you may express this as a telescoping sum, it might be easier just to do the limit. While you may express this as a telescoping sum, it might be easier just to use the limit comparison test. Let's compare it to the sum as n goes from 1 to infinity of 1 over n squared, which is a p-series, p equals 2, which is greater than 1, and that implies that it converges. Now to apply the limit comparison test, we'll take the limit as n goes to infinity of 1 over n times n plus 1 times the reciprocal of this, n squared over 1. The limit is 1, and since this is a positive real number, we conclude that both converge or both diverge. Since we had convergence of the p-series, we conclude that this series converges. The next problem has the sum as n goes from 1 to infinity of n squared e to the minus n. This particular problem looks amenable to the integral test. We'll look at the integral from 1 to infinity of x squared e to the minus x. The method of integration is integration by parts, but because x is squared, we should use the tabular method. U is x squared and dv is e to the minus x. We differentiate down the first column until we get to 0, and we integrate down the second column. We multiply down diagonals alternating signs, plus, minus, plus. And so we have x squared e to the minus x, negative x squared e to the minus x, and then minus 2x e to the minus x, and then negative 2 e to the minus x evaluated from 1 to infinity. You can see that in the limit as x goes to infinity, and technically being an improper integral, we should take the limit as the upper limit goes to infinity, but I assume that you are savvy enough to figure out how that works out. As x goes to infinity, exponential decay will beat the polynomial growth, and we'll get 0. Subtract what we get when we plug in 1. That's going to be negative e to the negative 1, minus 2 e to the minus 1. That gives us minus 3 of them so far. And then minus another 2. That's going to be minus 5 e to the minus 1. Minus minus makes plus. This is finite. Both converge or both diverge. Since the improper integral converged, we deduce that the series converges. On the next problem, you are specifically instructed to use the integral test. So, let's go ahead and declare the test. We integrate from 1 to infinity, 1 over x squared plus 1 dx. Now, I required that you know the value of this integral. Well, I required that you know the antiderivative of this integrand. In particular, that's the one I wanted you to remember. That's the inverse tangent of x. Now, inverse tangent is like a tangent curve on its side. As x tends to infinity, the inverse tangent tends to pi over 2. And inverse tangent of 1 is pi over 4. Yeah, it's pi over 4. That doesn't matter. What matters is that you get a finite value, which means that the improper integral converged. Both converge or both diverge. Therefore, the series converges. We have the sum as n goes from 1 to infinity of 1 over n to the 1/2. This is a p-series, so you shall use the p-series test. P is 1/2, which is less than or equal to 1, and therefore the series diverges. The last problem was more a prelude to the present one. This is an alternating series, and we need to determine not only convergence or divergence, but we also need to determine whether or not convergence is absolute or conditional. So there's more work on alternating series problems. First of all, we may use the alternating series test. If we look at the function f of x equals 1 over the square root of x, which corresponds to everything except for the negative 1 to the n, notice that this function has derivative equal to minus 1/2 x to the minus 3/2, which is negative 1 over 2 times the square root of x cubed. For x values bigger than 1, this will be negative, which means this function is monotone decreasing. In addition, if we take the limit as n goes to infinity of 1 over the square root of n, we get 0. Those are the conditions for convergence for the alternating series test. We deduce that the series converges, but we're not done yet. We need to determine absolute convergence or conditional convergence. But in this case, the previous problem proves that the series does not converge absolutely, because in absolute value we had the previous problem. So I'm going to permit you to say, by the last problem, converges conditionally. On this next problem, we have the sum as n goes from 1 to infinity of 1 plus 1 over n to the power n. Some of you will recognize that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e and not 0. Therefore, this series diverges by the divergence test. Let's assume that you didn't know that this limit was equal to e. Or, on the problem on the exam, the limit perhaps won't be e. What do? This is a 1 to the infinity case, which is an indeterminate case. You can kind of see that there's no way the terms go to 0, so you should be using the divergence test. In evaluating this limit, the limit involves the standard trick of e to the log. That allows us to apply a property of logs that brings exponents out into the front. The limit can be brought into the exponent of the exponential function because limits pass through continuous functions. We'll express the limit as log of 1 plus 1 over n divided by 1 over n, flipping the n down here. This is all in the exponent. We now have a 0 over 0 case, which is a L'Hopital's rule case. Applying L'Hopital's rule, we have e to the limit as n goes to infinity 1 over 1 plus 1 over n. By the chain rule, we have to multiply by the derivative of the inside, which is negative 1 over n squared. And that's divided by the derivative of 1 over n, which is negative 1 over n squared. We get e, which is not 0, and therefore the series diverges. We have the sum as n goes from 1 to infinity of 2/3 to the n. You should recognize this immediately as a geometric series. The common ratio is 2/3. Since the common ratio has a magnitude less than 1, the series converges. In fact, it's possible to find what the series converges to in this instance. In the next problem, you are asked to calculate the sum of the infinite geometric series. The formula for the sum of an infinite geometric series is the first term divided by 1 minus the common ratio. The first term in this case is 1, and the common ratio is negative 1/9. We get 1 over 1 plus a ninth. 1 is 9/9, so we'll have 10/9 in the denominator. That's going to be 9/10. On the next sequence of problems, we're asked to find the radius and interval of convergence for various power series. We'll begin with the sum as n goes from 0 to infinity, negative 1 to the n, x minus 3 to the n, divided by 4 to the n. The center is 3. The radius of convergence is the limit as n goes to infinity. The formula is an over an plus 1, which is a kind of upside-down ratio test. Remember, we obtain this by dividing the ratio test off. So we get the limit as n goes to infinity. You can always ignore the negative 1 to the n because you're inside of absolute values. I'll put it there, but we'll cancel them off anyway. Yes, these go away. 4 to the n cancels, and the limit is 4. That's the radius of convergence. That's one of our answers. It follows that the interval of convergence contains everything from negative 1 to 7. The only thing left to check is convergence or divergence at each of these endpoints. At x equals negative 1, we'll have the sum as n goes from 0 to infinity, negative 1 to the n, we'll have negative 4 to the n over 4 to the n. This simplifies as the sum is 0 as n goes from 0 to infinity of just 1. This diverges by the divergence test. The terms don't go to 0. They stay at 1. At x equals 7, we have the sum as n goes from 0 to infinity of negative 1 to the n, positive 4 to the n over positive 4 to the n. That's the sum as n goes from 0 to infinity of negative 1 to the n. Again, the terms don't go to 0, so this diverges by the divergence test. We deduce then that the interval of convergence is not contained. It doesn't just contain this interval, it is the interval from negative 1 to 7, not including either of the endpoints. In our next problem, we have the sum as n goes from 0 to infinity, negative 1 to the n, x plus 1 to the n, divided by n plus 1 factorial. The center is, of course, minus 1, but it looks like, since we have a factorial in the denominator, this is going to have an infinite radius of convergence, which is easy to check. We'll take the limit as n goes to infinity. We can ignore the negative 1 to the n stuff. 1 over n plus 1 factorial times n plus 2 factorial over 1. We get positive infinity for the radius of convergence. We deduce then that the interval of convergence is the entire real line. Next, we have the sum as n goes from 1 to infinity of x minus 1 to the n divided by n times n plus 1. The center here is 1. The radius of convergence is the limit as n goes to infinity of 1 over n times n plus 1 times n plus 1 times n plus 2 over 1, which is 1. That implies that the interval of convergence contains everything from 0 to 2. The only question is, what happens at 0 and what happens at 2? At x equals 2, we have the sum as n goes from 1 to infinity. 2 minus 1 is 1. 1 to the n is still 1. n times n plus 1. This series behaves like a p-series with p equals 2. It behaves like 1 over n squared. We need the limit comparison test in order to make that comparison. We'll take the limit as n goes to infinity of 1 over n squared times n plus 1 over 1, the ratio of the two, which is 1, a positive real number, therefore both converge or both diverge. Therefore, this series converges. At x equals 0, we have the sum as n goes from 1 to infinity of negative 1 to the n over n times n plus 1. This converges absolutely because of our work for at x equals 2. Really, that's all you need to say. It follows then that the interval of convergence is the closed interval from 0 to 2. On our next problem, we have the sum as n goes from 1 to infinity of n plus 1 times x plus 4 to the power n divided by n squared. The first thing to observe is that the center is minus 4. The radius of convergence is the limit as n goes to infinity, n plus 1 over n squared times n plus 1 squared over n plus 2, which is 1. That means that the interval of convergence contains everything from negative 5 to negative 3. At x equals negative 3, we have the sum as n goes from 1 to infinity, n plus 1. Negative 3 plus 4 is 1. The power of n is still 1. Over n squared. Converge or diverge? As n gets big, the plus 1 doesn't matter. It looks like 1 over n, the harmonic series. This should diverge by limit comparison test to the harmonic series. So diverges comparison test to harmonic series. I'll let you get away with just stating that. It's pretty obvious at this point. At x equals -5, you see that we have the sum as n goes from 1 to infinity, n plus 1, -1 to the n divided by n squared. This series behaves a lot like the alternating harmonic series. It should converge. Conditionally, of course, but we don't need to state that for power series. This converges by the alternating series test. I'll let you say that. It follows then that the interval of convergence is everything from -5 to -3, including -5, but not including -3. The next problem requires that you calculate the Maclaurin series for the hyperbolic cosine function. A Maclaurin series is a Taylor series centered at 0. The way to proceed is to calculate derivatives. The derivative of cosh is sinh, and the derivative of sinh is cosh, so these will repeat after the first two. Since it's a Maclaurin series, we evaluate everything inside at 0. The hyperbolic cosine at 0 is 1. The hyperbolic sine at 0 is 0. So the coefficients are going to alternate 1, 0, 1, 0, 1, 0. Therefore, we have 1 plus 0 times x plus 1 times x squared over 2 factorial plus 0 times x cubed plus x to the 4th times 1 divided by 4 factorial, and so on. We'll write this in sigma notation as the sum as k goes from 0 to infinity. We'll have only even powers, and we do not alternate signs, so it's going to be x to the 2k divided by 2k factorial. You should notice that this is almost the same as the power series for the cosine function, the only difference being that the cosine function has alternating signs, -1 to the power k. The next problem says, use the error formula to find an upper bound on the error when using the Taylor polynomial of degree 6 centered at 0 to estimate the cosine of 0.23. The remainder formula, centered at 0, is the 7th derivative evaluated at some point z, x minus 0 to the power 7 divided by 7 factorial. Now, we don't know exactly what these, well, now, the 7th derivative of cosine is going to involve something like plus or minus sine. We don't know exactly where this number z is, just that it's between x and 0. X in this case is going to be 0.23, this value here. We need an upper bound on this. Sine gets no bigger than 1. So let's estimate this by 1. We'll have 0.23 to the power 7 over 7 factorial. Let's leave our answer as this. We are next asked to calculate e to the 5 minus pi I. This will use the famous Euler's formula that we spent some time proving. First, write it as e to the 5 times e to the minus pi I. It's at this point we use Euler's formula. E to the theta I is cosine theta plus I sine theta. And so we have e to the 5 times the cosine of minus pi plus I times the sine of minus pi. the sign of any integer multiple of pi is 0. The negative here is irrelevant because cosine is an even function, so these negatives go away. The cosine of pi is -1. So the answer is negative e to the power 5. The next problem asks you to state the Maclaurin series for e to the x, sine x, and cosine x. I want you to just memorize these. Commit them to memory. I also want you to express these in two ways. First, by writing out some terms, but I also want you to know the sigma notation for these. Sine x is an odd function. It only has odd powers. X, it alternates in sign. Its sigma notation representation is the sum as k goes from 0 to infinity, -1 to the k, x to the 2k plus 1, divided by 2k plus 1 factorial. Cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on, and its sigma notation representation is the sum as k goes from 0 to infinity, -1 to the k, x to the 2k, divided by 2k factorial.